Good evening. I'm yours truly, Professor Dr. Dolphy Gilpin. I'm here tonight, or in the evening rather, it's about 6:30 approximately, and we're doing uranium this evening. And let's just highlight it on a portion of our partial periodic table here. And you could see it's right here, U, atomic number 92, and atomic mass of this one look like 288.5, but we will look at it some more because we know we have a lot of isotopes, and that the atomic weight is the average weight of the isotopes, or the isotopic weights. But here's it. For certainly the atomic number is 92, that is 92 protons, and it looks like my writing is sometimes not too illegible, 288.5, but we will confirm it. Uranium. That's because it's in the actinide series, and in group, let's see what group it is in. We'll also certify the group for uranium. Okay. Okay, so here we are with uranium. Let's try to extract it from our deck, where we're not using this little notebook here, but another notebook tonight. Extract uranium from our deck here, and I think we'll be going on to plutonium. So simultaneously, we'll try to extract plutonium from, or separate it from our pack of 118 elements. And tonight, or this evening, I'd like to give appraisal and honor to one of my professors from City College there who taught me Chemistry 103. For that reason, I'm just going to do some significant number. For around that time, we had about 103 to 108 elements at the time in 1977, 78 at that time. 103 to 108 elements. Some of them were there but was not certified by the IUPAC, or the International Union of Pure and Applied Chemistry. So Professor Morrow, in a conversation, doctored me from way back there in the 1980s in a communication where I was requesting my grades and my for some medical reasoning, but the Professor Morrows, or Professor Dr. Morrows, which one is more relevant or in optimizing this chemistry, he doctored me at the time. So at this time, I want to really, and I will, give honor to Professor Dr. Morrows from the City College of the City University of New York, who instructed me in the course Chemistry 103 with the laboratory, in which I scored an A, and also Chemistry 108, which was actually done by Professor Radial at that time. But Professor Morrow was the one who did that. So I will be mentioning his name as I continue this chemical mission. So let's try to extract uranium at this time. Francium, one of the most rare things that has to be synthetically synthesized. It's not really available in nature, francium. This is lawrencium 103 for Chemistry 103, and this is uranium. We're going to use that tonight. radon, when we use the electronic configuration of uranium, that will come up. And when you get a chance, we'll be doing plutonium as well. So let's try to extract plutonium from the deck here. Here's plutonium, we're going to be using that. Radon, which comes up in the noble gas configuration of both plutonium and uranium, 103, and we're going to use 108 element, which is magnesium. Which one is that? Acium, I believe. Acium, HS. It's not here, so we'll get a chance, and when we get to that. But right now we're focusing on uranium. And I praise a lot of commendation to my professor at City College here. From way back in the 1970s, I did that course, and he doctored me, I think in the I went for my, what you call that thing there when you go for your grades, it was my total profile for all my courses, and during the communication he doctored me. Can't forget it. You must have been seeing something. So Professor Dr. Morrow, so he does have vision, and so I want to honor him at this time from the City College of the City University of New York. Okay, so here we are. We're going to be using 103, we're going to be using 108, and we get along to that. But at this time, uranium, 92 and 238. So there it goes, it's not 288, but it's 238 for the atomic weight of uranium, 238.13, an atomic number of 92. And the noble gas configuration of radon, Rn, something, probably about 5f36d17s2, 6s1, 7s2, something like that, 5, 6, 7. But we also will certify that when we get along. Let's look. Let's try to get our certification here from our notes in this electronic configuration or noble gas configuration of uranium. It's look like 5f36d17s2 for uranium, a silver white metal, atomic number 92, and atomic mass of 238.028, something like that. Yeah. Okay. So we say, in our introduction, uranium reacts with almost all the non-metallic elements except for some of the noble gases. And the reactivity increases with the temperature. And it reacts with hydrochloric and nitric acid, in which it's dissolved in these acids. When you do uranium, we must know that this is one of the elements that is used in nuclear chemistry a lot. And apart from its nuclear property, it does have its chemical properties. So it both have chemical and nuclear properties, which are sort of separated. Uranium. And apart from hydrochloric and nitric acid, we have that other acid attack the metal very slowly. Uranium reacts with cold water when finally divided. and it reacts violently with water and is extremely dangerous to humans. So when it's finally divided, uranium hexafluoride will react violently with water, and it's a very dangerous chemical reaction there. No isotopes of uranium-238 would be uranium-235. Uranium-238 is one of the most stable isotope of uranium, and I think it's found about 99.9% available abundance in nature. And the other isotopes are uranium-235. The isotopes of uranium-235 and plutonium-239. I guess in some decay of uranium you will get plutonium, but we'll also certify that as we go along. So we are doing uranium, but plutonium come up. Plutonium-239 reacts with fission explosively, and the fission occurs when the nucleus of the U-35 and the PU, the plutonium-239, is split open by neutrons directed at the nucleus. So when this neutron strikes the nucleus, then we have the fission process, and two other atom is born, causing the nucleus to be fragmented, releasing tremendous energy. So that's now getting into the nuclear sort of reactions. The reaction of uranium with water is exothermic and produces stoichiometric uranium dioxide or uranium oxide and hydrogen. And the reaction then proceeds to release hydrogen as it goes along. So first you get uranium oxide, uranium dioxide, UO2, and then as the reaction goes along, you get hydrogen being liberated and reacting with the uranium to form uranium hydride. And so the hydrogen then reacts with the uranium further to give you uranium hydride. So the reaction is now U plus H2O to give you UO2 plus hydrogen, and then it gives you uranium hydride UH. I think it gives you uranium-3 hydride as well, but we'll certify that as we go along. And some very inquisitive sort of look into uranium, as we are taught that uranium would be given a nuclear action with fire, but it doesn't. So if uranium is put in the fire, uranium powder will ignite and may cause a small explosion, but this is not the nuclear reaction as yet. Just the powder of uranium, like others. So I believe lead will do the same thing. I believe the powder of many metals will do something like that. Copper and all of those transition metals will also, if you put them in the powdered form, it will react violently or explosively to form the oxides. And here we have it. Fire does not cause or trigger a nuclear chain reaction of uranium. And uranium metal, when heated at 200 to 300 degrees centigrade, will react with hydrogen to form uranium hydride. And further heating to 500 degrees centigrade will reverse the process and remove the hydrogen from the uranium hydride. So that's a very interesting thing. You react the uranium with hydrogen at 200 to 300 degrees centigrade, and it gives you uranium hydride. And further heating to about 500 degrees centigrade, it removes the hydrogen and gives you back the at 500 degrees Celsius will reverse the process and remove the hydrogen from the aluminum hydride, which was uranium 3 hydride. Alright, we don't want to saturate a lot of information here. So we're going to take a break and we'll come straight back to our uranium. And once again, we know that it's in the electronic configuration we use radon, Rn, and also it's Rn 5f36d17s2 for the electronic or noble gas configuration. The electronic configuration Rn, and here I have the Rn 5f36d17s2. But we are doing uranium. So let's just put it here and we will take a break and return to uranium. We're at the point here with uranium hydride being formed, and then further heating, you get the uranium. Where is that? Yeah, the reverse process at 500 degrees centigrade, in which the hydrogen is removed from uranium. We will take it up from there and continue with our uranium.